Okay, my name is Sharon Majumdar. I'm a professor in the Department of Atmospheric Sciences at the Rosenstiel School. I'm subbing in for Dean Avisar, our normal host of the Sea Secrets. And it's my pleasure to welcome everyone on campus and also online to the final lecture of our 30th anniversary season of Sea Secrets. We're glad to have you join. As for Dr. Jon Zawislak's lecture, the title of that is Into the Eye, the Science Behind Hurricane Hunting. And next we'd like to take a moment to thank our Sea Secret sponsors, without whom this excellent series would not be possible. Our presenting sponsors are Norwegian Cruise Line Holdings Limited, and we also appreciate our other sponsors, the Shepherd Broad Foundation, Bill Galway III, Cheryl Gold, KB Life Enhancement Forum, Key Biscayne Community Foundation, Joan McCoran Family Foundation, Nicole and Myron Wang, and Southern Glazers Wine and Spirits. And we know many of you are in the audience and very much appreciate your contributions. So before we hear from Dr. Zawislak, we're continuing our tradition of spotlighting exceptional alumni and graduate students. Tonight, I have the pleasure of introducing you to Alexis Wilson. Alexis is a current fourth-year Ph.D. candidate at the Rosenstiel School in atmospheric sciences. She's pursuing research in tropical cyclone formation in the Western Atlantic region, and her work is supported by the Rosenstiel School and a grant that actually Dr. Zawislak won as part of a NASA competition for grants. So that's been used to support Alexis through her time here. Alexis graduated with a bachelor's degree in Earth and Atmospheric Science from the Georgia Institute of Technology in Atlanta. She's also the current president of Canes on Canes. Canes on Canes is a student-led outreach organization. It's aimed at helping educate our community about the science of hurricanes and also hurricane preparedness. Outside of work, Alexis enjoys beach volleyball, science fiction TV shows, college football, and spending time with her cats, Rosby and Zira. Welcome to the stage, Alexis.
Thank you, Sharon, for that introduction. Hi, my name is Alexis, as Sharon wonderfully told all of y'all about. Here today, I'm going to talk to you about the 2022 NASA CPEX Field Campaign. Now, while we'll hear from Jay-Z plenty about all of the flights and research that we do going into the hurricane itself, there's a lot that we do flying into what we call African easterly waves, which are seeds in the atmosphere with a lot of clouds and a lot of spinning that can precede hurricanes from forming. So as part of this, we performed the NASA Convective Processes Experiment out of Cabo Verde, which is highlighted there, all the way right off the coast of Africa. Now, this is important because this is where we see a lot of these seeds coming off of Africa that downstream can eventually develop into hurricanes. Now, this campaign took place in September of 2022, which was peak hurricane season. A lot of the stuff we see on board the aircraft included scientific instruments such as that measured things like wind speed and the direction, things like humidity, temperature, even things like dust particles. We also had an instrument on board that could essentially get a radar image of what was going on below us. And this we get all the way from the plane down to the surface while we're flying. Now, during this campaign, we flew into 6 different African easterly waves, and 5 of these waves actually ended up developing into tropical cyclones. So we got a really good data set here. Now, I've talked a little bit about African easterly waves. Why are they important here? So African easterly waves are the precursors for around 60% of all Atlantic tropical cyclones. And I use tropical cyclones to mean anything from hurricanes or tropical storms. That's an all-encompassing term. Now, these waves have a lot of clouds in the atmosphere, and they travel through the Atlantic. They can become tropical storms and even spin up into hurricanes that may affect us here. However, a lot of these waves don't become tropical cyclones. So what our research flights can do that's different from the hurricane hunters, for instance, is we can help figure out TC formation. We can fly into these waves as they're coming off Africa and see why some of them might form and some of them might not. So how do these flights work? So before we go out, we have a lot of meetings. We're trying to figure out what we want to target. We're looking at the forecasts, and this is in a data-sparse region. So there's not as much like radars and things that you would see here in the US because it's just a tiny island in the middle of a great big ocean. So we have to rely on models and try and figure out what might be going on. And as we approach the deadline before we go and fly out, we have a go, no-go. Once we decide, yes, we're going to go, we get in the air. And it's a big, large event. There are people in the plane that are helping run the instruments, making sure they're properly calibrated and that they're all working. We have people on the ground, which you can see on the top right, the ground ops. We're looking at the real-time satellite data and adjusting the plane track in real time, trying to target some of those cloud systems that we see. And we have even people processing some of the data from things like dropsondes, which can measure things like temperature, relative humidity, wind speed, as they fall to the ground from the plane. And after the campaign, we take all this data, we clean it up, and we do some data analysis to look at it. So we're going to be a little bit of scientists here for a second and take a look at just a snapshot of one of the storms that we saw here. So this is Research Flight 7. This is an African easterly wave, which later became Hurricane Ian. We flew into it on September 16th in the early morning hours, and it ended up developing 7 days later all the way in the Caribbean. So we're going to take a look at this right here, which represents one of the real-time adjustments we made because there was this burst of cloud, deep convective activity that we were trying to fly within and see what was going on there. So pause for a sec. I know this looks like a lot. This is something that we would look at here and kind of the plots we would make. This is a combination of a few different instruments here. On the top, all of those really bright values, those are from the radar that we see. Now, when you look at your phone, a lot of what you're going to see is more of a horizontal view. You're looking at what's going on across the entirety of Florida, for instance. Here, it's coming from the plane as it's traveling along. So we get a more vertical, almost cross-section chunk to look at what the structure of the whole thing looks like, rather than just the average strength of all the convection across all of Florida, for instance. Now, we can see on the top here the region around 1750, that's the time. So up around here, you see that region of really strong convective cloud activity. That represents very, very heavy rain and a very mature system. And this can bring a lot of moisture from the surface where it's very, very moist, as I'm sure all of you here in Miami know. It can be very moist outside in the tropics, and bring it all the way from the ground up into the atmosphere. Having that really moist atmosphere is very important because it supports more of these kind of cells, more cloud activity, and as those come together, we can get a tropical cyclone. Now on the bottom, we can see this actually tells us what we call vertical velocity, how much those particles are traveling up and down. Now in the system itself, a lot of the cloud is going to be raining out, as you would expect. But in the mature system, you can see a lot of that vertical upward motion bringing that moisture air up into the atmosphere. And outside of that, we see these contours and colors right there. That's showing the relative humidity. So we can see it's a very deep, moist atmosphere here. And in part, that promotes some of that deep convection, while at the same time, that deep convection promotes more moisture. So it's almost a feedback loop. And so having these cross sections into the storm can help us get a better idea of what that atmospheric wave looks like and how it might progress later as we go through. And it became Hurricane Ian in this case. So thank you for your attention. And I would love to hear from Jay-Z.
Thank you, Alexis. Your accomplishments demonstrate the outstanding opportunities that are available to talented Rosenstiel students such as yourself. Next, it's now my pleasure to introduce tonight's speaker, Dr. Jon Zawislak. I'm not used to calling him John. Everyone calls him Jay-Z, so we'll refer to him as Jay-Z from now on. So all his friends and colleagues, it's Jay-Z. So Jay-Z is a meteorologist and flight director at NOAA's Aircraft Operations Center. Jay-Z's a veteran hurricane flyer. He's flown over 200 passes of hurricane eyewalls in the NOAA P-3 Hurricane Hunter aircraft, so just a few bumpy rides. He has a combined 15 years of experience in academia and at NOAA's Hurricane Research Division, researching hurricane formation and intensification, using decades worth of aircraft and satellite data. During that period, he also led several large aircraft field programs for NOAA and for NASA. In 2023, Jay-Z joined the NOAA Aircraft Operations Center. He applies his meteorological knowledge, his leadership, and field program experience to brief aircrews for mission flights. And he works with the pilots during the flights to safely maneuver the aircraft through the storms to achieve the mission and science objectives. The Rosenstiel School collaborates with NOAA in many areas of research and greatly benefits from close relationships of hurricane research and also for other aspects of oceanography and other sciences that NOAA does. Jay-Z, I'm especially delighted to welcome you to Sea Secrets, and to everybody be prepared for an educational and an entertaining ride.
Thanks, Sharon. It was just kind of coincidence that you introduced me because you're just substituting, but we've been friends and colleagues for quite a while now, so exciting to have Sharon, exciting to have Alexis here as well because her research is awesome, first of all. So really looking for her future, getting this Ph.D. done, where she's going to go. She's got a really bright future. And that campaign is very exciting to me and for Alexis as well because it was my last project I did before I moved on to the Aircraft Operations Center and really humbled to be able to lead that kind of a project in a faraway location for some very important science. So just a little bit of background about myself in a second here, but for me, this hurricane hunting business has kind of been a dream of mine because I got growing up to get into aviation. I loved flying. I love the weather. Okay, so to find this sort of intersection that I'm at now of actually flying aircraft into weather for purposes of understanding weather better is really exciting. So it's really been a dream of mine. So to be able to talk about this is really exciting. And for me, when I was thinking about what I wanted to do for this talk, it was, well, I was a scientist for many, many years, as Sharon said. So I could show this more plots. I could give you an hour worth of plots, I'm sure, to talk about hurricane processes and stuff like that. I don't know that that's what you want to hear about for now. You probably want to hear about flying hurricanes. So I decided to give you a little bit of what I would call, what we call the hurricane ground school. So in a couple weeks, I'm about to teach all of our pilots how to fly in hurricanes. They know how to fly. I don't know how to fly. I did fly a little, but you don't want me flying a hurricane. I shouldn't be anywhere near those controls. But I do talk about how to fly the weather of a hurricane. And so I'm actually going to take some of the content that I'm presenting in a couple of weeks, and you're going to see it in form as well, just to show you it's actually pretty simple. Not really. So as Sharon said, my background is a lot of aviation and using aircraft to study the atmosphere. So I was fortunate to be able to do a number of field projects, mainly at NASA up until a number of years ago working for NOAA. on the hurricane side, flying on the P-3 aircraft to sample the storms. So I sort of moved seats up front. But I have a lot of background in flying storms, so it's been very exciting to sort of evolve in my career from that top left when I was just a wide-eyed grad student 2 months into grad school and being asked to go to Cabo Verde to fly easterly waves. This is not her project. This was back in 2006. It kind of came full circle for me in the research. I started in Cabo Verde, and then I ended in Cabo Verde before going to the job. But doing a number of jobs in the aircraft, but certainly I think flight directing has been one of the more exciting jobs that I've been able to do in the hurricane business. Okay, so the number one question I get is what it's like to fly in a hurricane. Okay, so how many of you have been airsick? You can raise your hand, it's okay. I'm not gonna do anything. We got one, we got a few. They're starting to come up. Okay, there's a sign-up sheet, you can't fly with us. I need to know your names. Okay, I just need to know your names, okay? I wanna make sure we vet our list a little bit. Believe it or not, it's actually not that bad. You're probably actually gonna be bored. If we put you on board and put you in all the weather, unless it's like a Cat 4 or 5, you're probably gonna say, what are you doing to me and why are we out here for 8 hours? Okay, it's actually not that bad. I like to say that we're kind of normalized. It's about 75% of the time, it's not that bad. It's bumpy, it kind of gets a little frustrating once in a while, but there is a small percentage of time, is what you're seeing on the screen here, when it does get rather, you might call it horrifying, we might call it kind of fun, whatever you want to call it, right? We've had things go down the aisleway, float down the aisleway, and you get kind of bumped around, right? But we joke around, but the reality is it is a pretty long day, and you do get these situations where it gets quite turbulent. And the crew, we're very well prepared for it. We do a lot of training. We do a lot of preseason training, as we're doing right now. So we're a very well-prepared crew. The joys of the job, in addition to maybe a little bit of the roller coaster, and I always describe it as like the Tower of Terror. You don't know when the drop's coming, you don't know when it's coming about, right? It's a little bit of like that. But just that occasionally you get these kinds of views, right? And these are all the stadium effects, so to speak, where you get the clear bowl of cloud around you. These are all Cat 4s and 5s. Those are my 3 Cat 5s right there. Most recently, Milton, which was my first sub-900 millibar storm. If that means something to you, you're probably saying, oh my goodness, that's awesome, right? It may not mean a lot to you, but it's a really low-pressure storm. I think the 4th or 5th strongest storm on record in the Atlantic. So you really get these views, and it's really quite remarkable, and it's quite breathtaking. And the airplane's loud, but you hear this breathtaking, like, oh my goodness, this is a really incredible view. But there is a reason we do it, right? And this is the reason that we do it, okay? We love our job. We love being able to collect the data, help the science, right? At the end of the day, we're trying to help the communities. That's why we go fly. That's why we collect the data. That's why we try to improve models. We try to improve our understanding. It's because we know the reality is that these storms are probably going to make landfall. And these are all just recent. These aren't old images. These are recent images from Helene, right, from Milton, and from previous storms. So we do this for a reason, and we know the importance for why we're out there flying these storms. So before I get into how do we fly these storms, I want to walk you through a little bit of what it is that gets us to this point, okay? So I'm showing an track image here of Hurricane Helene, which I think if you're familiar with the hurricane, that was obviously a very devastating storm. It wasn't just a landfalling event for Florida in the Big Bend region. It also dropped a lot of rainfall in the Appalachian Mountains in the southeast and caused quite a bit of devastation that they're still recovering from. So this is just an example of how we actually kind of get started. So typically what's going to happen is they're going to go down and we're going to find some sort of disturbance. The Hurricane Center is going to see an area of cloud, like Alexis was saying, right? It's a disorganized area. It looks like it might be getting its act together. We may have some model runs, right? These model runs may be saying, well, we're looking at potential U.S. landfall, right? And this could be days. This could be a week ahead in advance. And so they're starting to get interested. Well, this might be something that's going to impact people. So let's consider maybe getting an aircraft into it so we can start getting the observations, start understanding what it looks like, trying to get that data into the model. So the Hurricane Center will become interested, and what they're going to do is make a phone call, and that phone call is going to come to CARCA. That is the Chief Aerial Reconnaissance Coordinator, all hurricanes. So it's a civilian Air Force unit at the Hurricane Center, and what they'll do is they're responsible for coordinating the hurricane flying. So they'll take the Hurricane Center requirements, how often they want to fly, when do they want to fly, what do they need, what data they need, and they'll call CARCA, and then CARCA will call us, or they'll call the 53rd, which is another Air Force, or another Hurricane Hunter unit at the Air Force Reserve in Biloxi. So they'll give us a phone call, and then we're essentially going to go start flying at the frequency and rate that we need to accomplish the observations. So This is just an image of all the flight tracks into Helene from all the aircraft, our P-3s. We have 2 P-3s. And then we also have a Gulfstream aircraft as well. It flies higher altitude. You don't see those flight tracks, but they're in the little symbols there for drop-zons, which we'll talk about later. But between us and the Air Force, we'll fly every 12 hours initially, and we may get down to pretty much continuous operations in a storm like Helene within the day or so before landfall. And what we're doing is collecting observations, and we're going to talk a little bit about some of those observations. But what they're doing is they're feeding analyses, right? They're feeding wind analyses, rain, surface waves, all those key hazards that you worry about when a storm makes landfall. We're creating observations that create analyses to understand the broad picture of that storm. And then all those observations we collect from the airplane go to models. So models will take that data, and the goal is to make the initialization of the model better, because if we make the model look better at the start, the assumption is we make the model better as it goes in the forecast, right? So we're going to simulate those observations, and then the Hurricane Center is going to absorb those observations as well, and all those analyses, and they're going to start to issue the public products. So this is as the storm's getting closer and closer to landfall. So those public products are some of those on the left. Okay, the storm surge product, what kind of storm surge we may experience as we get closer to landfall, the time of arrival for tropical storm winds, the track graphic that you're pretty familiar with, I'm sure. So we'll start to get those public products, and as it looks like there may be inland impacts, you might see some other operational centers at NOAA get involved, such as the weather forecast offices, the Storm Prediction Center, the Weather Prediction Center. This is just some graphics from the heavy rainfall event that was forecast for Helene. This was before all that rainfall dropped, warning people that we have a potential catastrophic flooding event. And so after all this is going on, we're still flying, the products are coming out. We might get some key messages that you're going to see. Those key messages are issued by the Hurricane Center and the weather forecast offices, tell you to basically digest what's happening, what's going to happen, right? And then from there, the last link in all this, right, is the emergency managers, is the preparation. We've flown, we've gotten the observations, we've improved the models, the specialists have gotten at the forecast, we've advised the public, and now we need to disseminate that information that comes out to you to how to prepare. Okay? So it's 3 links in the chain. It's 3 huge links in the chain. It's the operation side, it's the flying side getting the data to help improve it, and then it's the emergency managers, the media getting the word out. So all these links in the chain are really critical. That's what keeps this operation going. But there is one other component. I see a few research friends here in the audience, and that is the research. Okay? So this whole process that we do here is all based in the research that's been done previously. Okay? Understanding storms, building better models, building forecasts, and even the social science, right, which I know University of Miami's been, and Sharon's been involved in. That's really important. How do we communicate best so that people know how to react and understand the storms? So now, how do we fly a hurricane? Okay, the best answer is we do it as safely as we possibly can. Okay, right? That's the first thing. We carry a minimum crew of about 9 people. Okay, so we have 3 pilots, 2 flight engineers. The flight engineer is the gentleman there in the middle there who's working the throttles. Myself as a flight director, the meteorologist on board, so my job is to help us get through the storm, understand what the weather we're actually flying in. We do have a navigator because I can't do math very, very easily, and that's just what it is. So they tell us how to get there. And then we've got some engineers in the back who are releasing all the sondes, mounting all the instrumentation and such. But believe it or not, there's only one person really flying the airplane. That's the person in the left seat. The right seat pilot is actually the aircraft commander. They're monitoring everything. They're communicating with me, the navigator. They're communicating with the flight engineer, the crew, to just monitor safety. He has his hands on the controls. He's just mimicking. But the person in the middle is actually one of the most important people because that's the flight engineer. Their job is simply to maintain airspeed. We maintain 200 knots indicated airspeed at all times. That's our turbulence penetration airspeed. So if the airplane loses all of its airspeed, he's going to go ahead and push that throttle forward. If we gain too much airspeed, he's going to pull the throttle back. If at that point he's got it all the way to the firewall or all the way idle, then we'll start using the airplane pitch to actually gain back that airspeed. And they're communicating. It's actually quite remarkable how much communication is required to fly through the eye of a storm. So now I'm going to take you to a storm, and we're going to talk a little bit about the pattern. Okay, so what's going to have happened about 3 hours before I'm going to get in. It's probably 1 o'clock in the morning. I'm very grumpy at 1 o'clock in the morning, but that's the way it is. They accept that. I get 1 hour to prepare a brief. I'm going to create a weather brief that's going to basically brief the arrival weather or the departure weather at the airfield, the arrival weather, the en route weather, and what the storm looks like. I'm going to brief the crew. I'm going to say, hey, this is what the storm state is. This is what we expect. And then I'm going to go ahead and brief the pattern. What are the objectives of the flight? So we're going to go out and we're going to start flying. We're going to fly. It could be a 2-hour flight to the storm. It could be a 3-hour. It could be 20 minutes. But either way, we're going to set up a leg. And that first leg, in this case, is a west-to-east leg through what looks like pretty much a Cat 4 or 5 hurricane. Beautiful stadium effect, beautiful eye. The first thing we're going to do is we're going to descend down. We're going to get our instrumentation ready. And we're going to hit their initial point of the pattern. That is that dot there. And we're going to release a dropson. That dropson is basically a little instrument package on an inverse camping tent. It's a little pyramid, right? So we drop that out of the airplane, and as it falls to the surface, we're going to measure temperature, pressure, humidity, wind speed, wind direction. And we're going to drop a lot of these out throughout the storm. So we've dropped that sonde at the IP, and then we're going to go inbound. We're going to go find the eye. Hopefully it's easy to find. It's not always easy to find, believe it or not. The weaker storms are sometimes you got to kind of hunt around a little bit. So we're going to go through the eye wall, which is the most intense rain and wind. We're going to go through the eye, go through the outbound eye wall, and then we're going to head outbound to the other side. It's about 100 miles in, 100 miles out. So as we're going along, we're dropping more sondes. So we're going to drop a midpoint sonde right about in here, and then we're going to drop an eye wall. I have a little pointer. Eye wall sondes, a center sonde, and then we're going to go outbound, same thing, midpoint, endpoint. At that point, we're going to go downwind. We're going to reposition for our next pass. While we're doing that, we're doing some data analysis. We're doing some data quality controlling, okay? So there's some really ridiculous-looking messages here, and even I can't really decode the one on the left out of the spot you do made. I'm probably going to get nervous, okay? But essentially, the dropsons we drop, we can generate messages. They're formatted messages. They go to the models. They go to the Hurricane Center. They can interpret that data. The message on the upper right, that's a vortex data message. It's basically giving the Hurricane Center an idea of what the storm looks like. What's the minimum pressure we observed? What is the eye characteristics? How big is the eye? What's the eye diameter? Is it circular? Is it closed? Is it open? Is it elliptical? We're going to give them the messages about the flight level winds inbound. What's the peak wind we saw inbound and outbound at the surface and at our altitude? Temperature, dew point, a little bit. So there's a lot of information we need to translate in real time, okay? The lower right is from a radar. We have a radar on board called a tail Doppler radar. It's in the tail of the airplane. And that's actually giving a 3D picture of the storm. And so the Hurricane Research Division across the street, they're actually taking this data in real time and processing it, quality controlling it, and getting that data to the Hurricane Center. And it actually goes into the models as well to help that initial representation of the structure. So we're processing all this data as we go along, getting off the airplane. If we're not, we kind of panic a little bit, and you better get off the airplane. We're going to reposition. We're going to do a second pass. And it's going to look the same, probably the same sort of sonde pattern. We're going to drop their endpoint or midpoint or eye wall sondes of the max wind, the center. We're going to head outbound, do it all again, right? And we're going to go do a third pass. We're going to reposition, same thing, doing a lot of data analysis. Now, this pattern you see here is called a butterfly. I mean, sort of. Right. 3 passes with 60 degrees between all the azimuths. We have other patterns. We have what's called a figure 4, which is 90 degrees. It's basically just draw 4, and that's what it looks like. We can then do that 4 again, except we rotate it 45 degrees, and we call that a rotated figure 4. So it's just about how many azimuths that you want and what kind of spacing you want around the storm. This is about a 3.5-hour pattern inside the storm to complete the butterfly. Now, we are a research laboratory on the P-3. So the P-3 is a 4-engine turboprop. We got a lot of room for instrumentation. The Air Force Reserve, they do a few things. We do a lot more than them. So we'll carry research instrumentation, which actually makes the flight a little more complicated than the one you're seeing here. Thanks, HRD. Thank you for doing all this. A lot of good data. Thanks, Gus. It's great because we are not only trying to measure the key aspects of the storm, we're trying to understand the storm, right? So that's going to require a lot more information than the basics that we're collecting on all the aircraft. So for example, we want to understand the ocean. The ocean drives hurricanes. It drives the energy, evaporates heat and moisture into the storm. So we will drop buoys. These are an example of a buoy you drop out of the airplane in a little free fall chute, or we have a little, almost like a shotgun shell externally, we can shoot this thing out. So it's going to fall to the ocean surface. It's going to measure the sea surface temperature, and then it's going to float down and measure the temperature and the salinity of the water. And then say, well, maybe we want to drop some additional sondes. So we might drop sondes over the ocean gliders. An ocean glider is mainly operated across the street at AOML and their partners, and that ocean glider is an autonomous vehicle that's measuring profile in the ocean too. So what we'll do is we'll drop the drop sonde. That's measuring wind all the way down the atmosphere to the surface. And what we're trying to get at is where the ocean meets the atmosphere. That's a key area where those interactions are happening. So we need the atmospheric observations, so we'll release the sonde over top of the ocean measurement to get that to understand more about that interaction. So we might do that in a variety of areas of the storm. There's sail drones. There's another autonomous vehicle that's actually driven into the path of these storms, and the same sort of thing, measuring that air-sea interface. So we might additionally fly over those, getting measurements over top of those. And then what's special about our airplane as well is we drop drones. So we can actually release these little tiny airplanes. This is a Black Swift. We can actually release that huddled up in that little buoy-looking tube that goes out of the free fall chute. It comes out of there, opens up, and actually flies to the surface. It's like a flying drop zone. Okay, it's measuring temperature, pressure, humidity, wind speed, turbulence, and it's just stepping down about 5,000 feet down to the ocean. We don't get it back, but that again is flying in an area we will not put the manned airplane. We've tried, didn't go too well to put an airplane at 1,500 feet in a hurricane, so we'll send these drones down to fly as well. So once you start adding in all these elements, right, it starts becoming a little bit more complex, and it's my job as the flight director on the airplane to manage all this. I have to manage this. I have to make sure we get these out, work with the scientists on board to make sure we get these in the right location. And then we might drop a bunch of eyewall sounds too, because the eye and eyewall interact with one another too. There's an energy transfer between the eye and the eyewall. So we want to make sure we get additional measurements in the eyewall. So now I kind of give you a little idea of what the pattern looks like. Now, how do we get there? Now, in order to avoid the worst of it, and I always just say, I'm just trying to find the best of the worst. It's all pretty crappy out there, but I need to find the best path. So we have a couple of radars on board to allow me to do that. We have a nose radar, which any airplane you've ever flown on has one of these. Okay, it's just scanning in front of the airplane, looking out, just scanning back and forth. Okay, so this is an example of the nose radar. You see the eye of the storm right here. This doesn't work right there. That's the eye. You can see the eye wall, right? And it's pretty basic. There's 4 colors. Oops, sorry. So there's only 4 colors. Basically, black is not much rain. Yellow or green to yellow to red is an increasing rain rate. Okay. The disadvantage of this radar is that's only 4 colors. I don't get a lot of idea about the gradient. Thunderstorms go from green to red really fast. That gradient's really important to me because it tells me how quick am I going to get in turbulence? How bad is that turbulence going to be? Okay. So what we'll do is we have another radar called the multi-mode radar. Now this is on the belly of the airplane. You can't really see it really well. That's the P-3. On that belly is a little M&M looking radome. In there is that radar, and it's scanning 360 degrees around the airplane. It's looking all around. Now this is an example of the imagery. If you compare that, same colors, to this, a lot more detail, a lot more detail. That really helps me to see the gradients getting into the eye wall. And there's another mode that's very helpful. I won't go too much into the surface surveillance. But this provides the detail, but there's a huge disadvantage with this radar. It's a smaller wavelength. When you get a small wavelength like that, it doesn't see through the rain as well. So it gets what we call attenuation. All the energy from that wave dissipates very quickly. So I can't see through the eye wall with the multi-mode, and I'll show you an example of that in a second. So there's a couple things that I surprise people when I talk about flying in a hurricane. First of all, you know what an eye wall is, I hope. It's basically that bowl of that cloud that surrounds the eye. But eyes have different characteristics. And so depending on the characteristics, it kind of drives how we fly. So we may experience a really steep sloped eye wall, like this one in Lane, where it's a Cat 4 or 5 and it's really steep. There's other ones, when you get big eyes, they kind of shallow out. Well, why is that important? Because we fly pressure surfaces. That's altitude. We call pressure altitude, okay? So we fly at 10,000 or 8,000 pressure altitude. Now, pressure in a storm is lower than its environment, okay? 950 millibars, whatever you want to call it, right? The standard atmosphere is like 1013. A storm might be 950, 940. So what's happening, in order to stay on a pressure surface, we actually have to descend in to follow it. So now eye wall slope is impactful. If it's a really shallow sloped eye wall, like the one I'm showing you here, 35-mile eye, really big eye, we're just going to kind of gently follow that pressure surface down to the center, and then we're going to gently follow it out. However, if it's a steeper sloped eye wall, say in this 8-mile wide eye in a really intense hurricane, we're going to descend a lot more rapidly in, and then we're going to ascend rapidly out into the outbound eye wall. So what does this really look like? It's a couple hundred feet in like a Cat 1. You really won't notice it too much in a Cat 1. In a Cat 3, which is these lighter colors here, maybe 1,500 feet is what you're going to descend. So I'm at 10,000. I'm going to finish at about 8,500 feet when I'm in the eye. In a Cat 5, like Dorian, which is a very intense storm, 2,500 feet is about the loss that we'll have experienced. And again, it's about the gradient, how steep it is. Those steeper ones have big gradients. We're going to descend 2,500 feet in a pretty small distance. And you will tell on the airplane that you're doing so. You're about to find out why. You're going to get a visual representation, okay? This is really exciting. So there was a storm, Hurricane Patricia from, I think it was 2015, in the East Pacific. It remains the strongest hurricane ever flown by the NOAA P-3s. And that storm had a central pressure of 879 millibars. That's equivalent to being 3,000 feet in the air, okay, at the surface. So what you're going to see in this video is actually a visual representation of what it's like to fly in a Cat 5, and you're going to notice that descent rate. So I'm going to go ahead and start the video a little bit in. You're in the eye wall at this point, so you're inbound through the eye wall. You're heading to the eye, and what you're going to see when we merge into the eye is not the other eye wall. You're going to see the ocean. Okay, again, we're descending on the pressure surface, and because it's so low of a pressure and so steep and so angled, we're going to see the ocean out the window. Okay, a little disconcerting, right? You emerge into the eye, you think you're just going to see a bunch of cloud, maybe some clear sky, but what you're actually pointing at is the ocean surface. So you can see all the waves down below, you can see the other eye wall, the far eye wall. So we are descending. That airplane is pitch nose down. And then what you're going to see is we're going to start to level out as we bottom out on that pressure surface. And my job is to find the center. So I'm now calling, I'm not on this flight, I wish I was, but the flight director is calling tracks to the center. So those are those turns. We're waiting for the winds to come down to 0, and we're waiting for the wind flip from 180 degrees from my left to my right. So we're calling the pilots, track 135, track 138, track 140, in order to find the exact center of the storm. And when we do that, we're then going to turn and find our outbound track. And now you can kind of get a sense, there's actually a really nasty storm kind of developing the eye wall here. So the flight director is actually moving the airplane a little bit over to the right to get an outbound track. What you don't appreciate from this video, right? We came down really steep. What you don't get a sense in this video is we're ascending very steeply as well. Okay? So this is a dramatic representation of one of the lowest storms, pressure-wise, ever flown with the P-3. So a little disconcerting, but also pretty cool. They didn't think it was pretty cool after they did this outbound eye wall, because then they had to clean the airplane up and the computers broke and they just came home. It didn't work out great for the people who were, the flight director on there was his first solo flight directing flight. He started with a Cat 5, he ended with a Cat 5, so it worked out well for him. Yeah. So we're not only descending, we're trying to stay perpendicular to the wind. The safest way to fly a hurricane is perpendicular to the wind. The problem is it's hard to stay perpendicular to the wind as the winds pick up. So in order to do so, we're going to crab the airplane, right? So if I want to fly a track that way into the storm, I'm actually pointing the airplane this way, and we're just going to drift, right? It's like a car drifting. The higher the winds, the more we have to nose into the wind, but we're still going to track. So in this example, we call it the drift angle. I want to go this way, but in order to do that, I have to point into the wind looking this way. When we go outbound, it's the other direction. Instead of pointing this way, I'm going to be pointing this way because the wind's off my right. Does that make sense? Yep. Kind of make sense? Good. So let's say I have a 135 track. That's 135. That's a northwest to southeast pass through this eye wall and the eye. And this is what it's going to look like. I'm going to be pointing more and more and more and more to my left, going into the eye wall. And then as the winds come down, I'm going to level out. I'm going to be pointing straight because I got no wind. I'm going to the other eye wall, and I'm going to be looking more and more right. All to remain on the same exact ground track, right? And in a Cat 5, 160 knot flight level winds, we're going to be crabbed 40 to 45 degrees. So we're literally going to be looking 45 degrees that way, but I'm going that way, okay? The pilots get it. And so we're not only that, we're also descending. So we kind of look like this going in, and we kind of look like that going out. And you can feel it in a Cat 5. You definitely feel that dramatic effect. So just a little bit of matching up the radar to what you're seeing here in terms of drifting. This is that nose radar again, looking out in front of the airplane. Now our display on the nose radar is where the nose is pointing. We call it what's heading stabilized. So wherever the nose is pointing is where that 0 line is on our display. The problem is we're looking that way, right? So what you're seeing is in this radar display in Hurricane Dorian, and I was fortunate to be on this flight, although I don't think the flight engineer enjoyed it. His hands were a little shaky after working those throttles for 3 hours. But right now, the heading, we're pointing at the eye wall. The nose is pointing at the eye wall inbound, right? There's the eye. Well, we are actually tracking to the eye. It just looks like we're pointing at the eye wall, okay? And the other aspect that we have to understand as a flight director is the colors here. So there's this storm, you see more reds as we get closer and closer to the eye wall. The storm's not getting more intense. It's just that's a volume. The radar goes out as a beam and it has a volume. So as we get closer and closer and closer, the volume goes down. So if I take a really large raindrop and look at this and average it in this big volume, it looks really low. But as I get closer and closer and closer, right, now it fills that volume more. So the storm's not getting more intense. It's just that we're getting closer to the eye wall in that heavy rain. And then comes what kind of frustrates us once in a while. This is the nose, and this is plane. You can see this thing scanning. Well, this is the MMR, that little 360-degree scanner below the airplane. Where's all that outbound rain? It's not there. Except it is there because I see it on the nose. I can see it's a full eyewall. It's a Cat 5. That's that attenuation. It's sending the beam out. It's interacting with all this really heavy rain in this eyewall, but it can't see through it, right? So and we always say, I promise you, there is a really intense eyewall out there on the other side, but you just don't get a sense. So just a couple snapshots here, just working inbound. You can see what that attenuation of that radar is doing. I don't get a good sense, but I can see my eye. I'm tracking in this way, even though I'm pointing that way. And then when we get into the eyewall, I get a really good picture on the nose still, but that MMR is not giving me a really good picture. All that rain is attenuating. And then when we get into the eye and I start clearing out around me and I got that clear, guess what happens? Well, I can see the eyewall, but the eyewall is so intense, I don't see anything outside the eyewall. There is rain. There is a hurricane outside this donut. We call it the ring of fire. It's out there, I promise you, but it's all we see is the eyewall. Okay, so that attenuation and using those two radars is what they ask us to do, is to take the advantages and disadvantages of each one of these radars to best interpret what's in front of us. And I can't wait until it's only 10 miles away. I have to do this 40 or 50, 60 miles away, right? I got to give them a 10, 15-minute lead time in order to navigate this storm. Now, hurricanes, we talked about we're descending in, we're crabbed in, and we got to find the center. The problem is not all hurricanes are these beautiful, clean, circular eye walls. They get kind of gnarly and disfigured at times. And this is probably the best example. I flew this storm. This was a Category 4, rapidly strengthened very quickly. This is a 5-mile eye. For us, that's just about over a minute of being in the eye. But if I were to show you this picture and call that an eye, you'd probably say, get out of this building. Right? That doesn't look like an eye, but it is. And but what's in there is all these little notches. All these little notches. These are mesovortices. So the eye can break down. You think it's this beautiful, perfect circle. It's not. It will start breaking down into little tiny circulations. And those are enhanced reflectivity, enhanced rain, updrafts, downdrafts, enhanced horizontal shear, and all that's turbulence. That's the gist. So all these little tiny mesocirculations, this is turbulence. And then you can see Hurricane Lane here, Cat 5, beautiful 15-mile eye. But then here's another 15-mile eye, Hurricane Michael, right before landfall, and you can see all these notches. We call it kind of a wave number asymmetry. My job as a flight director is to try to guide us through that because we know we're going to get enhanced turbulence in those mesovortices. So we can avoid them, we're going to try. Here's a bigger eye, and then just occasionally you get fortunate and you get an 80-mile eye that doesn't even fill the radar. And just for perspective, that's that one on the left, same scale, right? We're in that little one for 1 minute. We're in this Nigel eye for 20 minutes, right? So we have to adapt to that environment. And maybe something we expected going inbound is not the exact same thing when we actually get there and said, oh, it rapidly strengthened, it's contracted to 4 miles. I thought I was going into a 10-mile perfect circle. Instead, I'm going into that one in the middle. So we have to adapt to that situation and get the airplane through it safely. Some more examples of breakdowns of eye walls is what we're calling the scallops these days. Okay, they're not like scallops potatoes. Those are really good. This is really bad. This is Hurricane Ian before it made landfall in Fort Myers. Okay, this is Fort Myers Beach. It made landfall as a Category 5. This is the radar, that MMR. It's looking around the airplane. I talked about attenuation. This is all it sees. The rain is so heavy in the eye wall that we can't see more than a couple miles around the airplane. The problem is if I don't know what I'm going into, I know I'm going to the eye. We're tracking into the eye here. They get absolutely rocked in this one. A lot of side to side, a lot of up and down. It remains one of the most turbulent flights ever flown on the P-3. And they had no idea that they were going into that, right? And the reason is because that attenuation, even the nose radar didn't have this little detail in the eye wall. When they finally got into the eye, this is what they found behind them, right? And it's these little scallops. This is where the eye and the eye wall are really strongly interacting with one another. It's really high shear. It's really, really strong turbulence. They actually aborted this flight. They went through once and decided not to go back in again because the airplane was just too overstressed. We can fly 99% of the storms and we'll be fine. We'll chip some paint. We'll lose some paint. We run away from the airplane, the maintainers, before they get on board. We're out of here, sorry, right? But just occasionally you do over-G the airplane. And that's when we'll go home and inspect the airplane. This was one of those cases. So this is the eyewall mesovortices. Just a few more pictures of this. So you're in the eye of Hurricane Milton here, and you can see these little notches again. And I was a flight director on this flight, and my goal was to try to go right between them. But I have to keep track of them because this is a Cat 4-5. So these are rotating. These little tiny circulations are all rotating around the eye. So it's like playing catch-up. I've got to anticipate, is this going to be in my track? Can I get ahead of it? Most likely we're going to try to get behind it, anticipating when it's going to curve into our track. In this case, we're heading towards that southeast, like I showed you before. Probably my most exciting flight was that Milton flight when it was at 895 millibars. This is a 4-mile eye, so we're only in it for 1 minute. It's Cat 5, 895, 160 knot flight level winds. These notches are just all these little mesos, and I was watching this thing just spinning, all these little mesos just spinning around the eye. At that point, it's sorry about your luck, pilot. We're just going to go right through. There's nothing you can do about it, right? You're just going to go through it. There's nothing you can do about it. So I think it's important to talk a little bit about the measurements. Again, I used to be a scientist, so I really love talking about these measurements, but I just want to give you a little context for now we're flying through it. We've collecting a lot of the measurements. What are some of those key measurements that we need? Okay. The big one is the minimum sea level pressure because of storm intensity. How low is the pressure? Typically, the lower the pressure, the stronger the storm. Okay. It's really, really, really hard to measure surface pressure. Okay, we're not at the ocean surface. Those sail drones can help us. Dropsondes is primarily what we use to measure the surface pressure. We drop those things out of the airplane, they fall to the surface. The last measurement we get before it splashes is the surface pressure and the surface winds. So surface winds, right? That's what you experience when these storms make landfall, right? Is the storm intensity, is the winds. And we need to know them all around the storm, which is the strongest quadrant. Where are my strongest winds? Really hard to measure surface winds. Okay. Now you say, well, why don't we use a satellite? Satellites don't have any idea, all right? They just don't. It's hard to measure surface winds alone from an airplane or an instrument on this airplane, let alone from space. So this is still the best we got, and we're getting better. But appreciate how hard it actually is to measure surface wind, and all around the storm as well. So we have things like dropsondes. There's something called the step frequency microaviarometer. It's a passive instrument just looking at radiation from the sea foam generated by waves. We could take the flight level winds. This is an example of what you see here, really strong winds in the center of the storm. We're going to reduce that to the surface, or hurricane center reduce it to the surface. We have the Doppler radar. So there are ways to get it, but it's very hard to measure completeness directly. Storm size matters. That matters for shear, or for surge. It matters for how far away from the center am I going to experience tropical storm winds, hurricane force winds. The precipitation, obviously, is really critical. We want to know where the strongest rain is. We want to know the asymmetries of the storm. If I'm on this side, am I going to get more rain on this side, right? Matters for severe weather. When it makes landfall, you get supercells, you get tornadoes. Milton was a great example. Probably if you live down here, you probably experienced potentially some of those tornadoes from Milton's landfall. And of course, the flooding. The number one killer of storms is not the wind. It's the flooding. It's the rain, the inland flooding, the surge. Right? So we have to understand a little bit about that flooding potential, which is involved to the ocean wave height. And we don't measure anything directly with operationally, but we contribute research instruments on the airplane who can measure this. And there's always new technologies being developed for ocean wave height. And I added this one because I think it's probably maybe one of the more exciting research directions we've had in the community, which is looking at the alignment of the circulation. So the center's here at this altitude. Where's the center as we go up in the atmosphere? And why that matters is because if it's tilted, it's kind of hard to organize a storm that has a center down here and the other center above is 50 miles away, right? But what we're seeing is that as they become more aligned, that can sort of kick off those really strong rapid intensification events. So our airplane has a tail-up radar on it, and that's a great tool. We're getting a three-dimensional picture of the wind and rain. We can actually see that circulation with height and look at the trend, and then that trend can be fed to the Hurricane Center, and then they can anticipate a little better as when maybe shear is taking that circulation and actually getting aligned. So it's a really exciting result, and I think it's a little bit new maybe if you've been in this community, because I think it's where we need to go as a predictive measure for some of these more intense, rapid strengthening events. But I mentioned it's really hard to measure intensity. We measure it continuously with the step frequency microaviarometer. Again, it's kind of looking at the sea foam and the radiation for the sea foam that's being generated. But other than that, we just have to release dropsondes. We will try to release dropsondes in the eyewall in the center and have them float down to the surface and get that surface wind. But it's really hard to do. Okay, we're flying, the storm's moving, the wind's going to move it. So we might come inbound. Don't worry about the text up top. I'm going to show you right here. My goal is to drop it in the peak wind at flight level, and it's going to start falling to the surface on that parachute. It's going to drift with the wind. Just occasionally, you actually nail it. It will drift, and it will just stay in the eye wall. It'll stay in the peak wind, and we hit the peak wind. Most of the time, it doesn't happen. It's hard to do. Look, it's hard to do. Don't interpret my ability to drop a max wind. It happens. Sometimes it ends up inbound. You might get into a mesovortex like this, and it ends up inside the eye. Sometimes it'll float outside the eye. I might try to drop a center sign right there at the exact center of the flight level wind, but it's tilted, so I get a 30-knot wind to the surface. It's really cool when you drop a sign right in the exact center. It's like 1 knot at the surface. It's really cool. It's really fun. But you can just see it's a very dynamic atmosphere. Those eyes aren't perfect. We talked about all the circulations that are within them. It is really hard to get the exact centers. Those mesovortices, all these little tiny swirls and stuff you see, these are potentially little low areas of pressure, and it's hard to target that, particularly for the smaller eyes. So what analysts have to do, and all specialists at the Hurricane Center have to do, they have to understand the context. Where did I drop it? Where did it end up? We know where it drifted to, but you have to understand the context of the measurements. That's really, really important, understanding all the context for the measurements. So one last measurement before I kind of close a little bit on a couple of things here. The tail Doppler radar is really what makes us at NOAA and our Hurricane Hunter aircraft unique. So here's the tail section of the airplane. There's 2 antennas that kind of look like this in there. They're looking forward and aft of the airplane. And what it's doing through some math that I just can't do, and if you do it on the spot again, I'll be embarrassed. But it basically connects the 2 antennas, and you can do some math and back out wind, right? It's like your Doppler radar in CT, like Alexis mentioned. It's getting a 3-dimensional wind. So we can actually slice and dice the storm at will. So this is just 3 different altitudes slicing through. You can see this is the wind speed down here. Look at all those pinks and whites. Those are really high winds. And then all the range. So we're slicing and dicing. We can do vertical profiles. Basically, every time we pass through the center of that storm, we are providing a 3-dimensional picture of the eye, right? And that's a remarkable, remarkable measurement. And not only that, we can accumulate all of them together and get sort of a composite picture. Once you do all the passes, you can see the composite of a butterfly here. And all this data is going to the models, the high-resolution hurricane models, right, that are developed at HRD. And it's the reason why we're getting intensity so good now is because those high-resolution hurricane models are already good at representing storms. Now we're adding actual data, like from the TDR. So it's a really significant advancement that's really helping us predict storms better. And overall, one of the last few messages I want to leave you with, again, is going back to those links in the chain. The research is a core link. I'm a little biased because I was there, but it really is. All papers like this, everything that we collected. We've been flying hurricanes for over 80 years. Okay, 1943 is the first one. Tell you that story over other things, but almost immediately after that, we were flying a hurricane reconnaissance. We've been developing data sets for decades. So you can mine those data sets, and we're still learning. We're still getting new advancements. We're still developing new data sets, new technologies. And the researchers are really serving to understand the processes, the forecasts, and then translating that into actually how do we communicate these important things to the communities who are now going to be impacted by it. So all these new technologies, like the drones we're dropping out, or new types of dropsons, those are little like styrofoam cups that we release out. We can launch a bunch at a time. This is a Doppler wind LiDAR setup where we can actually measure winds in clear air. Those radars measure things in rain. Well, there is clear air in hurricanes, and we can measure winds in that clear air, right? So now when you start putting all these technologies together on our laboratory, our flying laboratory, we can start putting that picture together and really understand what that storm looks like, right? And feed that to the models. We can validate models, right? We can say, well, this is how we can improve it. And what all this technology and all this research is leading to is the future, right? Those are future technologies. The reality of NOAA is our airplanes are aging. Our P-3s are aging. We've got 5 more years in those P-3s, and we got to replace them. We only have 1 more year at the G4. So this is the future of NOAA right now, is replacing our Gulfstream airplane with a brand new Gulfstream 550, a couple of them, and then moving the P-3s to the C-130 air. And this is really hard to do because airplanes aren't meant to carry instruments. So we actually have to modify these airplanes. And so we're in this process of learning how to modify a C-130 to, say, carry that tail Doppler radar. You don't put that tail radar on the C-130. We have to figure it out, right? So this is the future for us at NOAA. And what I really want to emphasize, I've got 2 more points here. One is I talked about flying the hurricanes. It sounds really fun, but I enjoy it because of these guys, right? These folks. It's all the people you get to fly with. And if there's anything you take away from tonight, other than cool pictures and Now you know we descend in and we're crabbed and everything like that. It's the people that do this, right? This is a really hard thing to do. And I can't speak any more highly of the people that I've flown with, whether research, the folks on the aircraft, the pilots, the navigators, the engineers. It's a really remarkable group who are really dedicated to getting this right, no matter what it takes, right? No matter what, as long as we do it safely, that's what it takes. But it's a really, really dedicated group, and it really has been an honor to fly with all those folks who really just want to help communities prepare, right? That's what we're out there for. And what I always say is, I will keep doing this job every day of the week, all night long. The 1 a.m. missions, I will keep doing it as long as you guys prepare. As long as you take the information that's given to you, right, to prepare for a storm, that makes this worth it. So heed the watches, heed the warnings, heed the public officials, be prepared, because that's why we do this, right? If you stop doing that, I'm going to stop, right? But I'm not going to. It's a lot of fun. But it is April, right? It's almost May. Hurricane season is upon us. So I want to end with this slide. That QR code takes you to some really good information about hurricane preparedness. Please be prepared. 1992 was an inactive season. Don't worry about seasonal forecast. 1992 was an inactive season. What happened in 1992? Andrew, right? Don't worry about the seasonal forecast. We always say it only takes one. It only takes one storm. So be prepared for whatever that season may bring. Be prepared. This will help you learn where do you get me information, how to prepare during a storm, how do I adjust from when I get impacted by a storm. So please prepare. Hurricane Preparedness Week is May 4th to 10th. With that, I will end.
All right, awesome. Yeah, thank you very much, JZ. That was a very spectacular and very detailed overview about everything to do with flying in hurricanes. So yeah, I guess that most of you now feel like you're ready to fly in a hurricane. There's a lot of steps to get through, or maybe some of you are scared about it too. Okay, and yeah, in all seriousness, thanks to JZ and you many colleagues at NOAA for all that you do in keeping South Florida and the nation safe. And so next we'd like to turn it over to you as part of a question and answer session. And so I'd like to introduce Jennifer Dillon to come up. Jennifer is our Executive Director for Development at the Rosenstiel School, and Jennifer will run the show from here.
Thank you so much. I tell you what, thank you so much, John, for all that you do. I tell you what, I praise that you go out there and do that for us. I wanted to say thank you for our sponsors. Thank you, Alexis, and thank you, Sharon, for doing this tonight, and to all of our sponsors who sponsor Sea Secrets. We couldn't do it without you. Sponsorships help us put this show on, and one of the things I wanted to mention, today is Earth Day, and it's really important for our students here. One of the things that we do to recruit the best students to our school to come and do this kind of research is we can offer them some scholarships. So if you would like to help us raise some funds for our students for the scholarship fund, our opportunity fund, or you could name your own fund if you'd like to. You can speak with me, Jennifer Dillon. You've got my email up here. And our students come here to do research in several different areas, from saving lives, feeding the world, unlocking ocean secrets, and protecting our marine resources. So today's Earth Day. No better time than today to help support our students here. Now we'll go forward and take some questions. And I'm going to have our students go through, and if you'd like to ask a question of John, please raise your hand, and he'll point you out, and we'll go from there. Thank you.
Actually, so many questions to ask.
Good.
For those, for example, sail drones, and don't they get destroyed pretty quickly and all that?
Actually, no. They've been directed into Cat 4s. We're talking 120 mile per hour winds, 100 mile per hour winds. They get knocked around a little bit, but they do survive it, and they're really taking pretty incredible measurements continuously of wind speed, pressure. So they survive surprisingly well.
And is it, one more, as all these later hurricanes, they seem to intensify so much faster than in the past. Is that also with alignment, or do you
It
measure
is,
that?
yeah. We've seen, unfortunately, a number of rapid strengthening events, very notable ones, and our worst nightmare is when they happen just before landfall, right? You went to sleep with a Cat 1, you wake up with a Cat 4 or 5, right? And if you haven't prepared for Cat 4 or 5, that's really challenging. But we are finding, the research is really finding that there are symptoms of it, and we think that alignment of the circulation, if we can detect it, and it's hard, right? You got to go in there and fly it. But if you can do that, that sort of triggers, potentially, that might be the trigger for it. And so we see that, we're doing a lot of things that are symptoms of processes. We can't measure them directly, but we're measuring symptoms, and I think that's one of them.
Why do y'all only fly over the ocean? Why do you not fly over hurricanes during their time over the land?
Mainly, it's hard. I mean, the instruments are a little impacted by them. So we don't drop sondes over land. I understand when they fall, they're not going to hurt tremendously with the parachute, but they might otherwise. But even the radar gets a little bit impacted by that. And generally, at that point, while the impacts are really high, we know they're also weakening. And a lot of times during season, keep in mind, we're flying one storm. As soon as it makes landfall, we may have to start focusing on the next one. And so, especially in September, we're going storm after storm after storm after storm after storm, and we do need a day off now and then.
Does the size of the eye in any way correlate to the strength of the storm? Like, does the eye get larger? Does the storm get stronger?
It's not one-to-one, but generally, if you have a really small eye, it typically happened through processes that made it really strong. And those really small eyes, like those 4 or 5 mile eyes we fly through, they're pretty unstable. Like the moment you kind of interrupt them a little bit, think about the ice skater, right? The ice skater pulls their arms in, they go really, really fast. It's going really fast, but if you just give them a little nudge, right, they fall over, or that just kind of discombobulates them a little bit. So it's kind of like that. Those smaller eyes do tend to be happening in really strong storms. The bigger the eyes, it's not exactly one-to-one at that point. It just depends on how stable the storm gets. There you go. Lots of questions.
Yeah, I thought it was very interesting about the information you get while you're in the storm, dropping all this. But my main concern sitting on the ground is this helping you know the direction that the storm is going to go,
Right.
where it's going to hit landfall.
Absolutely. We talk about some of those eye wall features and stuff. Those eyes are wobbling around a little bit, right? And so there's processes that we have to measure to understand what might take it from one direction to another. Now, what I didn't talk a lot about was the NOAA G4. That's a Gulfstream. It's kind of a business jet. That flies at higher altitudes, like 40 to 45,000 feet. We'll fly that around the storm. It doesn't go through eye walls really well, but we'll fly it around the storm. And the primary goal is to actually get those drop zones out ahead of the storm in the kind of things like a trough or something or front that's going to pick that storm up right before landfall. We want to get out there and get that airplane ahead of the storm, and that will help on that track forecast.
And why do they have to hold 200 knots exactly going through there?
So at 210 knots, that's our sort of stable flight profile. If we go any faster than that, if we get one little bump, we'll exceed what's called the angle of attack. That angle of attack is when you stall the airplane. So if we go too slow, we're going to stall. If you go too fast, we could also stall the airplane as well. And stalling isn't ideal in our... So I want to emphasize, stalling's fine when you're doing pilot training in clear air, not in a hurricane.
Thank you very much, John, for sharing tonight. Your enthusiasm for the work you do is very contagious. I'm wondering, as far as, I mean, you promised that you're going to keep doing this as long as we do our part, but to what extent do you and maybe the community of people that you work with feel like this is still, I mean, you've got a life, you've got a family and stuff like that you can still maintain and do this kind of work in light of like current situation? You know, can you still make a living for a while? Do you still have hope that you can do what you want to do?
I mean, here's what I'll say, and I think this question is what I always get is this, well, we got satellites, we can build these things, we can build these technologies, but the reality is the things that we're measuring, you need an airplane, right? And the drone technology, we drop those things, but they're only about that big, right? They can handle the turbulence, they can handle the winds down low, but they're not going to fly the 8 hours. They're not going to be in the storm for the 4 hours that we require. So we're really still moving the direction that we need a manned aircraft, right? We still need to develop the new technologies from it. So really in the near future, I don't see us replacing our manned aircraft with unmanned aircraft. We might be able to use an unmanned aircraft for like the G4 where you can fly really long, really high, stay out of the severe weather, but to put an airplane through it is really aggressive. So we're generally I believe in my lifetime, we'll still be flying manned aircraft in hurricanes. Sure.
Hey.
One more, and then I'm happy to stick around for a couple minutes.
So I have a quick comment. Hey, Jay-Z, over here.
Oh.
So you made a lot of very nice comments about the research collaboration. I just wanted to expand on that quickly. You know, at the Hurricane Research Division, you know, we have this experiment called the Advancing Prediction of Hurricanes experiment. And the AOC crew, and John in particular, do a fantastic job, I think, of balancing the research priorities with the operational needs that are there. And I think you undersold it just a little bit because we really put you guys through the paces because the research that we conduct is really important for setting the priorities and the innovations for what can go on future aircraft and help get those forecasts better in the future. And you know, in order to make that work, it's a really delicate balance. You showed sort of dropping us on over the sail drone, but as you know, we try to tack on research at the end, and it becomes an even more chaotic situation where you're balancing operational priorities and research. So I just wanted to take a minute to recognize that and thank you for balancing that. It's really, really important to the mission.
Gus and I have been friends in college for a long time too, and we used to work together, and he's right in that. And we don't do any of this, go back to the links, right? All those links in the chain, right? There's a reason that research link is in there, right? Because it's this complete package. We don't get to the end result without starting somewhere. So Gus and his colleagues and all the academia and all these federal labs, everybody's doing this work to try to get us to the point where that's actionable information. I'm happy to stick around for a couple minutes too.
Thank you so much.
Thanks.
We're gonna cut it here. If you want to stick around and ask more questions, he'll be here for a little bit. Thank you so much for attending the series this year, our 30th year. Appreciate it.